Okay, we're going to take a look at something called a confidence interval. And we're going to start with the ideal case where the standard deviation for the population is known. Now, I kind of like this cartoon, Dilbert. I don't know how to do statistics, but it doesn't matter because I didn't have data. So you actually will have little data for this to make it possible. Now, what is the point of this? When we take a sample or a survey or even do an experiment, we're trying to predict the mean for a population. Because we don't know it, instead we use the mean for our sample. Now, if we get an average of 17, does that mean our population average is 17? For example, let's say I surveyed teachers here at high school and said, how far do you drive to get to work every day? And my sample average was 17. Does that mean all the teachers at the high school drive an average of 17 miles a day as a population? And no, that's not going to be the case because there's randomness and variability to our measurement. Now, if I had to make a prediction of the average miles that these teachers had to drive to school, I would prefer to do a window instead of saying 17 exactly, because that's the odds of it being 17.0 are very low. Maybe I'd rather do a window of, say, 15 to 19 miles. So we call this window, if that's the window for our prediction. Now, if our data is normally distributed and we know the standard deviation, so that's the point of the lesson, we're actually going to know this, then we can know what percentage of data will fall within our window. And we're going to call each half of that window our margin of error. So in the example I said, the average miles driven would be 17 plus or minus 2. My margin of error would be 2. We call our window a confidence interval. And I'd say, oh, okay, my confidence interval is 15 miles to 19 miles. The width of our window is going to depend on how confident we want to be. For example, if I wanted to be 100% confident, I could say, oh, 0 miles, and I'm pretty sure nobody's more than 100 miles away. I could even say 1,000 miles, which you know is impossible for them to drive to and from work. But that's not going to be a very impressive prediction, all right? So we're going to actually use our confidence to define what's called the critical value, Z star. Sometimes you'll see this in lowercase, sometimes you'll see it in uppercase. I tend to switch. It doesn't matter. So first, let's recall the empirical rule. 68% of the population lies within one standard deviation of the mean. 95% does lie within 2. But I'm going to show you that we can actually make a teensier, tinier, tighter prediction because technically it's 1.96. Will it make our prediction that much tinier? No, but every little bit helps. 99.7% of the population lies within 3 standard deviation, and my critical value would be 3. Again, why wouldn't we want to use a 100% confidence interval? Well, to be 100% confident, we would have to include the entire range of possible values, which isn't very useful. Now, when we're doing a confidence level, we're looking at the middle of our normal distribution. That's where we're predicting. And the critical value, Z star, is going to fence it off on the lower end and on the upper end. So how do we find this critical value? If you recall, we learned the inverse norm function, which only uses the area to the left of the critical value. All right. And we were doing some problems where I would say, okay, 90% of the data is to the left of Z. What is Z? And you would do inverse norm of 0.90. And we'd say, okay, 20% of the data is to the right of Z. And you would do inverse norm of 0.80. But then we did some other problems where the middle, like 80%. What did we use for Z? Well, we kind of taught you this before. For the middle, you do 1 minus whatever that percentage is, in this case our confidence level, and divide it by 2. Why is that? Well, if you have 80% in here, how much is left that's outside? Well, that'll be 100% minus 80%, which is 20%. And I'm going to have to split that from here to here. So that would leave 10% for the left and 10% for the right. I could discover what this value is right here by doing inverse norm of 0.10, which is the easy way to do it, and you're going to get a negative, which is why this absolute value is here. Or I could actually do inverse norm of 0.90 to get the positive Z value. Either one works, and I know most of you prefer the shortened formula. So let's go ahead and do the most popular confidence level, which is 95%. So we're going to do inverse norm of 1 minus 0.95 over 2, or inverse norm of 0.025, and we get z star is 1.96. That's the one I mentioned earlier. This is used so frequently, it is worth memorizing. And note that it's not inverse norm of 0.95 or inverse norm of 0.05. It has to be this 1 minus 0.95 over 2. It would actually work if you did inverse norm of 0.975. Why? Well, we have 0.025 here, 95% in the middle, or so 2.5% here, 95% in the middle. So on the left of this z value, it's 97.5%. But honestly, this shortcut works pretty well. Remember, you will get a negative when you do it. All right, so don't use just the confidence level or 1 minus the confidence level in inverse norm. So let's go ahead and calculate the critical value for a 99% confidence level. We're going to do 1 minus 0.99 divided by 2. So it's 0.005 or 2.58. For a 90% confidence level, it's 1 minus 0.9 divided by 2. So you have 90% in the middle, 10% left over, 5% on the left, 5% on the right. That's where the 0.05 comes from. And that's 1.645. As the confidence level increases, the width of the confidence interval also increases. Remember, if I want to be 100% confident, I just say everything, which makes a super wide interval, which is not so impressive. So once we determine a critical value, then we can multiply it by its standard deviation to determine how far we're going to go out in each direction. And this distance is called the margin of error. So you have a margin of error here, and you have a margin of error here. This middle value is your point estimate, what you think the value is. And basically, how do we find that? It's your critical value times your standard deviation. So to get the lowest value of the confidence interval, if I go back to this picture up here, if I want to know this value right here, I'm going to get my mean from my sample, my point estimate, and subtract this margin of error. So we'll subtract the margin of error. If I want to get the high value, I would add the margin of error. So you find that basically it's going to be your statistic or point estimate plus or minus your critical value times your standard deviation. Recall that our goal is to make an estimation of mu based on our sample. So we're actually going to be using X bar. X bar is for a sample, mu is for a population. So let's look at this example of shrews. And we're going to say the average weight of 100 shrews in a recent study is 5.45 grams. Based on previous studies, we can assume that the weights are normally distributed with this standard deviation. And I want to find a 95% confidence interval. So what critical value should I use? Well, I want the middle to be 95%, and that leaves 5% left over, so 2.5% for here. And so 1 minus 0.95 is 5%, divided by 2 is 2.5%, and I get that 1.96. Technically, if you had memorized it, you could have just said, oh, it's 1.96. What standard deviation should we use? Well, we're dealing with sample means, so we're not going to use 0.08 exactly. We're going to divide it by the square root of the sample size. So it's 0.08 divided by square root of 100 up here, which is 0.008. My margin of error is my critical value times my standard deviation for the mean, and I get 0.01568. So if I wanted to find the lower limit, I'm going to take my mean, my point estimate, and subtract my margin of error. And I get this, 5.45 minus 0.01568, well, roughly 5.43. And if I want to find my upper limit, I just add it, and I get 5.47. So what does a 95% confidence interval really mean? First of all, intervals have the form your estimate, often called the mean in this case, your point estimate, plus or minus your margin of error. All right, so that's the form. Our confidence is in the process of constructing the interval, not in any one interval. So here are a bunch of confidence intervals for different samples. And you can see if this yellow line represents what the actual value is, we're fairly confident that several of these will capture it, not necessarily the one we did. So it's in a 95% confidence interval, we expect to capture the population parameter in 95% of our intervals. That's what it means. So let's go ahead and look at some ways to interpret it. There's a 95% chance that the interval is one of the intervals that contains the true average weight of shrews. Or 95% of the confidence intervals created using this method will contain the true average weight of shrews. So that's how we tend to word these.